Hello, everyone. Today, I'm happy to be here to present our recent work on transcription-free filler word detection. So first of all, what are filler words? In linguistics, the fillers are the sounds or the words that people use to signal that they are pausing to think during a daily conversation or spontaneous speech. Typically, the filler words can be divided into linguistic ones, such as like, and non-linguistic ones, such as ums and ahs. According to research, in American English, the most commonly used filler words are ums and ahs. These non-linguistic fillers are usually very short, and this is also the focus of our paper. In previous studies, the filler word detection problem was treated as sound event detection problem. More specifically, MSCC or other acoustic features are first extracted from the input waveform and then was input into a convolutional recurrent neural networks. At the output of the network was a frame-wise predictions on whether that certain frame is filler or not. The following were proposed to integrate an ASR system and a VAT system to detect the fillers. Usually, the ASR system do not transcribe non-lexicon fillers in the spontaneous speech, but the VAT system will be activated for the non-lexicon fillers. These different regions could possibly be the fillers, and they additionally train a classifier to classify whether it's filler or not. In this paper, they also propose an alternative method without ASR system for the situations where people cannot access to the ASR. If we look at the filler word detection performance of the ASR-based and ASR-free system, we can see that there's a huge gap. And this leads to the main topic of our work, how to bridge the gap between the ASR-based and ASR-free systems. If we look at the transcription-free systems, there is a potential problem here. In the second stage filler classification, it's usually a frame-wise classifier predicting the frame-wise labels on whether it's filler or not. And it usually involves a post-processing step that using median filtering or Viterbi decoding to turn this frame-wise predictions into event level. And the post-processor parameter tuning could influence the final performance. Here we show a concrete example. And after the post-processing step, we miss one true positive and still have two false positives here. So here's a question. Can we avoid the manual tuning and direct output the event intervals instead of aggregating the frame-wise confidence with some post-processing steps? Here, we borrowed in the idea from a method in the sequence tagging problem in the natural language processing called semi-Markov conditional random field. In such systems, the outputs are directly the segmentation of a sentence instead of the labels word by word. In the following, we will show how we apply this method into filler word detection. Naively, we will have a network that will map the waveform or its acoustic features into frame-wise embedding. We denote the input sequence as X with length n. It could be n frames of acoustic features. And we denote the output sequence with W. And for convenience, we also assume the length as n. We make use of the advantage of the semi-CRF, which directly output the event level labels. We turn this semi-CRF into a neural version into the neural network as a layer. To be specific, the frame-wise embedding W is fed into the score model that can compute a score for the segmentation of a sentence of a sequence. Suppose we have a event segmentation SI, which begins at time index BI and ends at time index EI with event label LI. And then we segment the whole sequence into P events. So S, capital here, is a segmentation for the full sequence. This network can actually compute the score given the frame-wise embedding W and this particular segmentation S hat, divided by a normalization term that takes the summation over all of the possible segmentations. We reach the final objective function of this likelihood. Training objective is to maximize this term. During inference, we decode this score using dynamic programming to get the segmentation of all of the events. Another important component is the neural network backbone for the frame-wise embeddings. Here, we use a structured state space sequence models. The S4 models are newly proposed neural network backbone that can model a long sequence. It is mainly inspired from the state space equations. On one hand, the state space functions can be written as a recurrent layer. On the other hand, it can also be written as a convolutional layer with a very long kernel. With this equivalence, the S4 layer is a convolution layer but can model a very long sequence in one single layer. Another important aspect of this method is that it utilizes the Legendre series to compress the sequence into a lower dimension. To summarize, in our method, we first introduce a neural semi-CRF layer to directly output the event level labels, and it avoids the post-processing step for aggregation of the frames. And secondly, we introduce the S4 models as our frame-wise embedding backbones. And this S4 backbones can do a better sequence modeling. It is shown that it achieves superior performance in many sequence classification and also generation tasks. And secondly, because of the Legendre series compression, the parameters in the actual model is actually very lightweight. In the experiment part, we train and test our method on the podcast fillers. For the front-end feature, we use a pre-trained wave-to-back frame encoders. And during training, we simply train event level filler classifier. And during evaluation, we integrate a pre-trained robust voice activity detection module and the trained event level filler classifier. And eventually, we output the events labels and together with its time steps. For evaluation, we use a widely used segment-based and event-based FOI measure. For the segment-based method, the event was put on a fixed grid and compare the ground truth and predictions. For the event-based metrics, the ground truth events and predicted events are performed a graph matching and compare the event onsets and offsets separately. To demonstrate the effectiveness of our proposed method, we first list two baseline systems with and without transcription from the previous paper. We see our system achieves both improvement on the segment level metrics and also the event level metrics. In the ablation study, to see the effectiveness of the neural semi-CRF layer, we compare a system with and without the semi-CRF layer. In the systems without the semi-CRF layers, we applied a post-processing using a median filtering on the frame-wise outputs confidence and tune threshold on the validation split. And from both figures, we see that the semi-CRF layer can achieve some decent improvement over the system without semi-CRF, except for the transformer. In the second ablation studies investigating whether the S4 backbone can achieve better results, we remove the semi-CRF layer and directly run the system. We see that the S4 backbone can achieve better performance. And in both of the ablation studies, we see that the transformer-based systems performs poorly on both of the experiments. This might be due to the small data set we use. And finally, this is a full outline of this presentation. I'm happy to take any questions. Thank you.